All right, today we're going to do something that might sound a little intimidating, but I promise it's going to be fun. We're taking a tour of your computer's memory. We're going to go under the hood and get to know one of the most powerful and, yeah, sometimes feared concepts in programming, C pointers.
So, think about this for a second. You've probably written a line of code like x equals 10 a million times, right? Doesn't matter what language you're in. But have you ever really stopped to ask, what's happening there? Where, in this giant digital world inside your computer, does that number 10 actually live? That's the question we're diving into today.
To really wrap our heads around this, we need a good analogy. So let's picture your computer's RAM, not as some abstract thing, but as a huge, sprawling, and perfectly organized cityscape. Every single byte of memory is like a building, and every piece of data you create has a physical location, a real street address.
Okay, so if memory is a city, then every variable we create has two really important pieces of info. There's what it's holding, and then there's where it's holding it. And in C, there's actually a special way to think about this, like a hidden address book for all your data.
C gives us two terms for this, L value and R value. Just think L for location, that's the L value. It's the memory address, the street address of the building in our city. Then you have the R value. Think R for read value, that's the actual content, the stuff that's inside the building.
So great, everything has an address. But how do we actually use those addresses directly? Well, C gives us a special tool for that exact purpose. It's kind of like a GPS for navigating our data cityscape. And that tool is the pointer. Now, a pointer is a really unique kind of variable. It doesn't hold a number, it doesn't hold text. All a pointer holds is a memory address. In our city analogy, it's like a little sticky note where you've scribbled down the street address of some other building. The note itself isn't the building's contents, it just tells you where to find it.
And to use this GPS, you really only need to know two simple operations. First, there's the ampersand symbol. Think of it as the address of operator. It lets you get the address of a variable. It's just like looking at building K and writing down its address on your sticky note, PTR. Then you have the asterisk. This is the dereference operator. It lets you follow that address. You look at the address on your note, you go to that building, and you see what's inside. So remember, ampersand gets the address, asterisk follows it. Simple as that.
Now, just knowing addresses is one thing, but the real, raw power of C comes from being able to go out and claim brand new, uncharted territory in memory whenever you want. This is where it gets kind of like the Wild West.
We do this with a function called malloc, which is short for memory allocate. Think of it like this. You're walking up to the operating system and saying, hey, I need a new plot of land, give me a raw block of memory, and just tell me its address. The OS then carves out a piece for you from a big, flexible area called the heap.
And this is the secret sauce. This is what makes C so incredibly flexible. You're not stuck with fixed-size variables you declared at the beginning. With malloc, you can build data structures of any size you want, right in the middle of your program running. You can build a skyscraper or a tiny shack, whatever you need, on the fly.
But as you can probably guess, with this incredible power comes some incredible responsibility. Because out here in the Wild West of memory, if you're not careful, you can make a huge mess.
There's one simple, golden rule. If you ask for memory with malloc, you have to give it back to the system when you're done. You do that using the free function. If you forget, well, that memory stays claimed by your program forever, even if you can't use it anymore. And that is what we call a memory leak.
Let's hop back to our city for a second. Imagine you go to the city office, you get a deed to a plot of land, you build a house, and then you lose the deed. You lose that one sticky note with the address on it. What happens? Well, the house is still there, it's taking up valuable space, but nobody can ever find it or use it again. It's just lost.
And this slide shows you exactly how that disaster happens in code. It's so simple. First, we create a pointer, stir, and tell it to point to a new 30-byte block of memory we just requested. Perfect. But then on the very next line, without freeing the first block, we ask for a different 60-byte block and point stir to that new one instead. Uh-oh. The pointer now holds a new address. The address to that original 30-byte chunk, it's just gone. Poof. It's been orphaned.
As one programmer on Stack Overflow put it perfectly, the first address is lost irretrievably. You have a memory leak. That abandoned block of memory is now a ghost town in your cityscape, just sitting there, taking up resources for absolutely no reason.
And you might think, oh, it's just a few bytes. But these leaks add up. A tiny leak in a loop or in a program that runs for days, well, it can slowly eat up megabytes, even gigabytes of memory until your whole application just grinds to a halt and crashes. It's truly death by 1,000 cuts.
So right about now, if you're a programmer who uses a more modern language, you're probably thinking, hold on a minute, I've never had to do any of this. And you're absolutely right. So let's connect all this back to the tools you probably use every single day.
I mean, really, have you ever wondered why you don't have to manually call free when you're writing in Python or JavaScript or Go? It's because those languages have systems that do all the dirty work for you. They basically have an automatic cleanup crew.
These safety nets usually come in two main flavors. First, you've got garbage collectors, or GC. You'll find these in languages like Python and Go. They're like little background processes that periodically scan through your memory city, find all those abandoned buildings we talked about, and automatically demolish them to reclaim the land. Then you have things like C++'s smart pointers, which are really clever objects that act like pointers, but they're programmed to automatically call free the very moment they're no longer needed.
So, here it is, the fundamental trade-off. The classic C-Way gives you blazing speed and total control over every byte, but it comes with a super high risk of human error, of memory leaks. On the other side, you've got these modern abstractions. They give you safety and automation by managing this idea of ownership for you, but they do add a little layer between you and the bare metal.
And that really brings us to the final thought I want to leave you with. Automation is fantastic, right? It's safer, it's more convenient, but it's worth asking, what insights do we miss when the machine hides its own mechanics from us? Understanding what C forces you to do, to really think about addresses, about allocation, about who owns what, it gives you this profound insight into how software really works. It teaches you to see the whole cityscape, not just the code written on the page.